I'm Mary Swarna Latha, working as assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the joint characteristic function and the joint moment generating function. So already in the previous lectures, we have studied about the characteristic function of a single and a variable x. So if you have a single and a variable x, then the characteristic function of that and a variable has been denoted by pi x of omega. So it's nothing but the expectation of e power j omega x, or else it is called as the Fourier transform of the density function of a random variable x. But in place of minus omega, you'll get here plus omega. So the same concept we are applying to the joint characteristic function for two random variables x and y. Therefore, the joint characteristic function of two random variables x and y is defined as the two-dimensional Fourier transform of the joint density function. And this joint characteristic function is used to calculate the joint moments of a random variable. For example, if you have two random variables x and y, and the corresponding the joint probability density function has been given by fxy of x comma y, then the joint characteristic function of the two random variables x and y is denoted by pi xy of omega 1 comma omega 2. Here x indicates the random variable x and here y indicates the random variable y, and the two quantities here omega 1 and omega 2 are the two variables here. So remember that here the omega 1 and omega 2 are not the frequencies, they are the variables. So is equals to what? Expectation of e power j of omega 1 x plus omega 2 y. If you have a single random variable x, then what is the characteristic function of that random variable x has been denoted by pi x of omega equals to expectation of e power j omega x. So here also, if you have two random variables, then the joint characteristic function has been given by expectation of e power j into omega 1x plus omega 2 into y. Now, what is the expectation of any function? How many random variables here have? Two random variables. Therefore, you have done what type of random variables you are taking? So, consider that x and y are continuous random variable. So, if x and y are continuous random variables, then the expectation of e power j into omega 1x plus omega 2y is equals to, since you have two random variables, I am writing the double integration. So, integration minus infinity, then nothing but x equals to minus infinity, and integration y equals to minus infinity fxy of x comma y into e power j omega 1 x plus omega 2 into y dx into dy. So how we are writing this expression? Because we know the expectation of any function. So expectation of any function nothing but what? That function. If it is in the case of continuous random variables, you will get the integration. So that function into the joint density function of the two random variables. Here x and y are the two random variables. Therefore, its joint density function has been given by fxy of x comma y. So into dx into dy. Now, for example, if I take the x and y are discrete random variables, then how can I do the joint characteristic function? Now, if they are discrete random variables, for the summation, instead of integration, I am going to use a sigma, nothing but summation. So, sigma fxy of xi comma yj. Here I am taking the two variables I and j, where I equals to minus infinity and j is also from minus infinity. Fxy of xi comma yj into what? E power j omega 1 xi plus omega 2 yj. So this is a joint characteristic function in case of what? The discrete random variables. And what is fxy of xi comma yj? It is also called as what? The joint probability, such that p of xi comma yj. So what is p of xi comma yj is nothing but what? P of xi comma yj. So it's nothing but what? P of x equals to xi and y equals to yj. The probability here, p indicates the probability. So the probability that the random variable takes x equals to xi and nothing but joint probability here, y equals to yj. Therefore, this is a formula for the joint characteristic function in case of continuous random variables and in case of what? The discrete random variables. Now, if you observe this formula, so what can you say that? This is nothing but what? The two-dimensional Fourier transform of what? The joint density function fxy of x comma y. Therefore, how can you say that? You can say that the joint characteristic function is called as what? The two-dimensional Fourier transform of the joint density function. Now, you know what is the joint characteristic function? Pi xy of omega 1 comma omega 2 equals to nothing but what? Two-dimensional Fourier transform of the joint density function of the two random variables x and y. Now, but in place of minus omega, here you are going to get what? Minus sign, you are getting a positive sign. And similarly, if you know the characteristic function, you can calculate the joint density function by taking what? The inverse discrete Fourier transform. Therefore, how can you find out the joint density function if you know the joint characteristic function? By taking what? Inverse. So, inverse two-dimensional Fourier transform of what? The joint characteristic function. What does it mean? You can say that the joint density function of the two random variables as well as the joint characteristic function of the two random variables both form a Fourier transform pair. It means the Fourier transform of the joint density function is equal to the joint characteristic function, and similarly the inverse two-dimensional Fourier transform of the joint characteristic function is equal to the two-dimensional the joint density function. But in place of the sign minus, we get here plus, and here in place of plus, we get the minus sign. Therefore, how can you write down the joint density function? Nothing but two-dimensional inverse discrete Fourier transform. So, what is the inverse Fourier transform formula? So, 1 by 2 pi square integration omega 1 equals to minus infinity and omega 2 equals to minus infinity pi xy of omega 1 comma omega 2, nothing but the joint characteristic function into what? E power minus j omega 1 x into e power minus j omega 2 y d omega 1 d omega 2. Actually, the inverse two-dimensional Fourier transform, in place of minus sign here we are going to get plus. Therefore, here but the sign is reversed. And similarly, in the Fourier transform also here you will get the negative sign. But for these two relations, the sign has been reversed. And coming to the properties of the joint characteristic function. So, what is the first property? States that the marginal characteristic function. So, what is the joint characteristic function you have seen? Of two random variables x and y, pi xy of omega 1 comma omega 2 is equals to what? Expectation. So, what do you mean by expectation? Expectation is nothing but what? Statistical average. This is also called as what? Mean also. So, the joint characteristic function is nothing but what? The expectation of the statistical average of the function. What is the function here? E power j of omega 1 x plus omega 2 into y. Now, in case of x and y are continuous random variables, then how can you write down this expression? So, integration minus infinity, integration minus infinity. So, whatever the function, that function you have to write down into the joint density function. So, the joint density function of the two random variables x and y, fxy of x comma y into what? Dx into dy. Now, what is the first property? We are writing the marginal characteristic function. So, what are the, already we have seen the marginal density functions of two random variables. For example, fxy of x comma y is a joint probability density function of two random variables x and y. Then, what are the marginal density function of x? So, fx of x is called as what? The marginal probability density function of random variable x. And what is fi of y is called as what? The marginal density function of the random variable y. Similarly, you can write down the marginal characteristic function of the two random variables x and y. So, what is pi xy of omega 1 comma omega 2 is called as what? Joint characteristic function. So, by keeping one of the variable to 0, in the joint characteristic function, you are going to obtain the marginal characteristic function. So if you want the marginal characteristic function of the random variable x, you have to keep omega 2 equals to 0 in the joint characteristic function. Therefore, what is phi x of omega 1 is equals to what? Phi xy of omega 1, comma. So if you want the marginal characteristic function of the random variable x, you have to keep omega 2 equals to 0 in the joint characteristic function. Therefore, that equals to what? Expectation of e power j into omega 1x plus this omega 2 equals 0 in case of the marginal characteristic function of y. Therefore, what can you obtain here? Expectation of e power j omega 1 into x. Similarly, if you want the marginal characteristic function of the random variable y, you have to do is in the joint characteristic function, you have to keep the variable omega 1 equals to 0. Therefore, if you keep here the joint characteristic function omega 1 equals to 0, then what is the expression you are going to obtain? Expectation of e power j into this term is 0. Therefore, e power j into omega 2 into y. Therefore, these two are called as the marginal characteristic function of the random variable x, and similarly the marginal characteristic function of the random variable y. And coming to the second property, if x and y are two independent random variables, then the joint characteristic function is equal to the product of their individual characteristic function. So, in case of x and y are independent random variables, then how we are saying that the joint characteristic function of the two random variables is equal to the product of their marginal characteristic functions. So, already we have seen that if two random variables x and y are statistically independent, then the joint density function of the two random variables is equal to the product of their marginal density functions. Similarly, you can write down if x and y are two independent random variables, then the joint characteristic function is equal to the product of their marginal characteristic functions of x, and here this is of random variable y. Now, how do you prove this? So, what is the joint characteristic function? Phi xy of omega 1 comma omega 2 is equals to what? So, phi xy of omega 1 comma omega 2 equals to expectation of e power j into omega 1 x plus omega 2 y. Now, if you consider x and y are continuous random variables, then how can I write down this one? So, expectation of any function. Since it is continuous, here I am writing the integration. Since you have two random variables, I am writing the double integration. So, that expectation of any function is that function into, since you have two random variables x and y, you have to write down the joint density function of those two random variables x and y. Therefore, pi xy of omega 1 comma omega 2 is equals to integration minus into infinity. So, integration minus into infinity e power j omega 1x plus omega 2y into fxy of x comma y dx into dy. Now, if they're independent, so if they're independent, what is the condition I said? The joint density function is equal to what? The product of their marginal density function. Therefore, you can replace this fxy of x comma y by what? Fx of x into fy of y. Now, write down the equation. Then pi xy of omega 1 comma omega 2 equals to what? Integration minus into infinity, integration minus into infinity. And how we are writing e power j omega 1 x plus omega 2 y as what? E power j omega 1 x into e power j omega 2 y, because e power a plus b equals to e power a into e power b. Therefore, simply can write down here e power j omega 1 x into e power j omega 2 y. And since they are independent statistically, we can write this as what? Fx of x into fy of y. Now, rewrite the equation. Then you are going to obtain like this. So, integration minus into infinity, integration minus into infinity e power j omega 1 x into e power j omega 2 y into the marginal density function of x, fx of x, the marginal density function of the random variable y, fy of y into dx into dy. Now, how can you rewrite this equation? You can write it as integration minus into infinity e power j omega 1 x into fx of x into dx into integration minus into infinity e power j omega 2 y into fi of y into, here this is only dy. So fi of y into dy. Now what is integration minus infinity infinity e power j omega 1 x into fx of x? So what is pi x of x, the characteristic function of the random variable x? For a single random variable you have say expectation of e power j omega into x. In case if x is continuous random variable, then how to write on this one? In case of continuous random variable, you have to write down integration. Since you have only one random variable, you are writing only one integration. So from minus to infinity, the expectation of any function is what? That function into the density function of that random variable x. So into what? Dx. So if you compare these two, so in place of omega here I have omega 1. Therefore, how can you write here pi x of omega 1? Similarly here, in place of omega here I have what? Omega 2. Therefore, we can write down this as what? So here pi x of omega. So this is nothing but what? Pi x of omega. Just in place of omega, here I have omega 1. And here in place of omega we have here pi omega 2. So this is for random variable x, therefore pi x of omega 1. This is for random variable y. Therefore this is nothing but what? Pi y of omega 2. Therefore you can write down the joint characteristic function of two statistically independent random variables is equal to the product of their marginal characteristic function of those two random variables. And coming to the third property, if x and y are two random variables, then the joint moments about the origin can be derived from the joint characteristic function as m suffix nk is equals to what? Minus j power n plus k into dou power n plus k pi xy of omega 1 comma omega 2 by dou omega 1 power n into dou omega 2 power k. After differentiating, then you have to substitute omega 1 equals 0 and omega 2 equals to 0. So what are the joint moments about the origin? You have seen m and k is equals to what? Expectation of x minus x bar power 0, nothing but x power n. Similarly, y minus y bar power k. So what is y bar here? 0. Therefore, expectation of x power n into y power k. This is called as what? The joint moments about the origin. This already have discussed in the previous lecture. Now, what is this formula actually? If they are continuous random variable, I can write down here integration minus infinity. Since you have two random variables here, I am writing the double integration. Okay. So, expectation of any function is what? That function into, since you have two random variables x and y, then its joint density function has been given by fxy of x comma y dx into dy. Now, if you know the joint density function, then you are calculating the joint moments about the origin. So, sometimes instead of giving the joint density function, if they give the joint characteristic function, then how do you calculate the joint moments about the origin? By using this formula. What is the formula here? M suffix n comma k. So, is equals to minus j power n plus k into dou power n plus k pi xy of omega 1 comma omega 2 by dou omega 1 power n into dou omega 2 power k at omega 1 equals 0 and omega 2 equals 0. So, after differentiating only substitute omega 1 omega 2 equals to 0. Okay. And what is the order here? The order of the moments is equals to what? N plus k. So, now we have seen the joint characteristic function. In the similar manner, the joint moment generating function is also to calculate the joint moments about the origin. Now, the joint moments about the origin of a single random variable we have already discussed. For example, if you have a single random variable x, then what is the moment generating function of that random variable x has been represented by m of random variable x. Therefore, mx of u is equals to expectation of e power u into x. In place of u, I can take any variable also or v also. So, mx of u equals to what? Expectation of e power u into x. So, if x is continuous random variable, then what is the formula? In case of continuous, and since it is a single random variable, we get a single integration. So, expectation of any function is what? That function into density function of that random variable. So, fx of x into dx. Similarly, you can write for the random variable y also. This is corresponding to single random variable. Now, I am considering two random variables. Therefore, I can write the joint moment generating function of the two random variables as what? Mxy. If you have a single random variable mx, or if you have a random variable y, my of v. But if you have a two random variables, you are written what? Mx comma y of u1 comma u2 is equals to what? Expectation of e power u1x plus u2y. Or else you can write it like this also. Expectation of e power u1 into x and e power u2 into y also you can write down. So because e power a plus b equals to what? E power a into e power b. So therefore this is called as what? The moment generating function for two random variables x and y. Now if x and y are two continuous random variables, then how can you calculate the joint moment generating function of the two random variables? So what is the formula? Since I am saying that these two random variables x and y are continuous. Since you have two random variables, I write down double integration. So x equals to minus infinity and y is also from minus infinity. So expectation of any function is what? That function nothing but e power u1x into e power u2y into what? The two random variable joint density function is what? fxy of x comma y into what? Dx into dy. Now, if the random variables x and y are discrete random variables, then how can you write down the joint moment generating function mxy of u1 comma u2 is equals to what? Sigma I sigma j. So e power u1 into xi and e power. So this is here not u1, this is u2. So e power u2 into yj into what? fxy of xi comma yj. And this fxy of xi comma yj nothing but what? P of x equals to xi comma y equals to y. Nothing but the joint property such that the random variable takes a value x equals to xi and the random variable y takes a value yj. Therefore, these are the formulae to calculate the joint moment generating function of two random variables x and y in case of continuous random variable as well as in the case of discrete random variables. So, we have written the discrete random variables joint moment generating function. So, similarly, how we written the properties for joint characteristic function in a similar manner, you can write down the properties for joint moment generating function also. So, how can you obtain the marginal moment generating function? So, by keeping one of the variable, either u1 or u2. If you keep u2 equals 0, then you are going to get the marginal moment generating function of the random variable x. If you keep u1 equals 0 in the joint moment generating function, you are going to obtain the marginal moment generating function of the random variable y. Therefore, by keeping one of the variable either u1 or u2 equals 0 in the joint moment generating function, you are going to obtain the marginal moment generating function. The short form for moment generating function is nothing but MGF. So, what is, if you keep u2 equals 0, then what you are going to obtain? You are going to obtain the marginal moment generating function of the random variable x. And if you keep u1 equals 0 in this joint moment generating function, then you are going to get the marginal moment generating function of the random variable y. And similarly, the second property is if x and y are statistically independent random variables, then you can write down the joint moment generating function is equal to the product of their individual or the marginal moment generating function of the random variables x and y. So, what is the second property? The states that what? If they are statistically independent, if two random variables are statistically independent, then the joint moment generating function is equal to what? Product of their marginal moment generating functions. And the proof of this can be done in a similar way as we have done for the joint characteristic function. And the third property is what? If x and y are two random variables, then the joint moments can be derived from the joint moment generating function. So, previously totally we are having three formulae. One is what? If you know the joint density function, then how can you find out the joint moments about the origin, nothing but what? Expectation of x power n into y power k. This is one formula. And what is the second formula to calculate the joint moments and the joint moments about the origin? So in terms of what? The characteristic function, joint characteristic function. So j power, so when j power n plus k into what? Dou power n plus k pi xy of omega 1 comma omega 2 by dou omega 1 power n into dou omega 2 power k at omega 1 and omega 2 equals 0. This is a second one. Already have seen this one. This is a second way to calculate the joint moments about the origin. And similarly, if you know the joint moment journey function of two random variables x and y, then you can calculate the joint moments about the origin by using the formula m and k, m suffix n comma k is equals to dou power n plus k into mxy of u1 comma u2 by dou u1 power n into dou u2 power k. After differentiating, you have to substitute u1 equals 0 and u2 equals to 0. And what is the order of the joint moments about the origin? Order equals to what? N plus k. So therefore, today in this lecture we have seen the joint characteristic function definition, and then we have moved to the properties of the joint characteristic function, then the joint moment journey function definition, and then we have moved to the properties of the joint moment journey function. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.